Alright everyone, welcome back for another episode of my Diesel 201 series. For anyone new here, the first video in this series was me going over Hyce's Diesel 101 video and adding a little bit of my own commentary. For this video I decided to actually put some effort in, but I still copied his 10 levels of understanding format he uses in his 101 videos, and we're going to be going over the 26L air brakes that I'm familiar with. 26L is a fairly ubiquitous type of air brake, and even the more modern electronic over air brakes still function in pretty much the same way as 26L on older locomotives. As we go through the levels, we'll mention several parts in the locomotive's air system. When I do that, I'll try and show a picture, assuming I could get one, so you guys can actually see what they look like, and we'll go over a little bit about what they do. There's plenty more detail on all these parts to come in the From the Rails Up series, but for now we'll try and keep it somewhat brief. And at the end of the video, we'll climb on an actual locomotive and go look at these parts in context. And to close out, we'll go through an example of an air test, and I also have a little bit of myth busting I want to do. So with all that out of the way, let's get into it. Alright, we're going to start out here at level 0. I'm going to assume that if you're watching this video, you know that locomotives use compressed air for their brakes, and you can also probably guess that air is used for the horn and maybe some other functions. You probably also know that locomotives have an independent and an automatic air brake, and you also might know that locomotives have two duplex gauges that allow the engineer to monitor the air brake system. You can also probably guess that if we use compressed air for our brakes, we need an air compressor in order to get that, and that's actually where we're going to start this video. Alright, so older EMD locomotives use a two-stage air compressor that is driven by the engine's crankshaft. The air compressor works by first drawing in air through either one or two filters, depending on the setup, into the two low-pressure jugs on the sides of the compressor. The air is then partially compressed in the low-pressure jugs and discharged into what's called the intercooler. The air coming out of the cylinders will be hot from the compression, so the intercooler has engine cooling water running through it to cool the air before it's drawn into the high-pressure jug on the top of the compressor for a second stage of compression. After exiting the high-pressure jug, the air will be at whatever main reservoir pressure is. Remember that the air compressor is driven by the engine's crankshaft. Because of this, the air compressor is turning anytime the diesel engine is running. To prevent the air compressor from building too much air pressure, it's equipped with unloaders that can be seen above the intake valves on each cylinder. When the main reservoir pressure reaches a set value, air pressure is sent to these unloaders. When the unloaders receive this air pressure signal, they descend and hold open the intake valves on each cylinder. This causes the cylinders to simply pull air in and push it back out through the open intake valves. This prevents the air from actually being compressed and delivered to the main reservoir. I'll also mention here that the intercooler has a 60 psi pressure relief valve on it. This relief valve vents air pressure from the intercooler in the event of some kind of unloader failure or something else going wrong in the air compressor. Because compressing air creates a lot of heat, the air compressor itself is also cooled by water from the engine. Typically, water from the engine's cooling water supply is pumped into a manifold, which in turn supplies water to all the air compressor jugs, the cylinder heads, and the intercooler. The air compressor also has its own lubricating oil supply with an internal pump and a filter on the side of the compressor. The oil level in the compressor can be checked with a dipstick, and the filter is changed at a periodic interval. So to summarize our level 1, older EMDs use a two-stage air compressor that is driven by the engine's crankshaft. The air compressor has unloaders to prevent it from building too much air pressure, engine cooling water supplied to it to dissipate the heat that it creates, and also has its own lubricating oil supply along with its filter. From the air compressor, the air goes to what the next level will be about, which is the main reservoirs. Alright, so we've got our air from our air compressor, but now we need somewhere to keep it until we need it. This is where the main reservoirs come in. Compressed air leaves the air compressor and travels through a long radiator pipe that allows the air to cool and ideally moisture to condense out before it reaches the first main reservoir. Air from the first main reservoir is used to operate things like the windshield wipers, sanders, horn, and crossing bell. The first main reservoir is also connected to the main reservoir equalizing MU hoses, which we'll talk about later. As such, When the locomotives are connected in MU, the first main reservoirs are all connected via these hoses. This allows all the air compressors in a consist to supply air to the lead locomotive. Near the end of the first main reservoir, there is also a 150 psi pop-off valve that will release air pressure to the atmosphere in the event of an air compressor failing to cut out properly. From the first main reservoir, the air passes through a check valve and enters the second main reservoir. Now, why is there a check valve? Well, remember how we just talked about all the first main reservoirs being connected through an MU hose? If a separation occurs, that MU hose will be open to atmosphere, which will cause all the first main reservoirs in the consist to dump their air to the atmosphere. To ensure that the locomotives still have air to stop, we use a check valve between the first and second main reservoirs to keep air in the second main reservoir in the event of a separation. Moving on, by the time the air has gone through the radiator pipe and sat in the first main reservoir for a while, it's had most of the moisture condensed out. As such, the air in the second main reservoir is ideally the driest. This is beneficial for preventing issues in the air brake system that can be caused by moisture, i.e. freezing. As such, all the air used in the air brake system comes from the second main reservoir. Now, the main reservoirs are usually equipped with some kind of automatic drain valve. There are different styles of automatic drain valves, because of course there are, but they all serve the same function, and that is releasing accumulated moisture from the reservoirs. If the moisture that condenses out from the compressed air were allowed to accumulate, over time it would decrease the volume of air that the reservoirs can actually hold. In addition to the automatic drain valves, each main reservoir also has an associated blowdown filter. These filters are typically located under the engineer's side of the locomotive and serve to capture any remaining moisture, oil droplets, or debris before the air gets into the cab and is used. These filters also usually have an associated automatic drain valve that will cycle just like any of the rest of them to remove captured moisture. Alright, to recap our level 2, air from the air compressor is passed through a radiator pipe to allow it time to cool and allow moisture to condense out. From there, it enters the first main reservoir. Air from this reservoir is used to operate ancillary components, like the horn, bell, windshield wipers, sanders, other things like that. Additionally, the first main reservoirs on all the locomotives in a consist are connected via the main reservoir MU hoses. This reservoir also has a pop-off valve to prevent excessive air pressure from building up. After the air leaves the first main reservoir, it passes through a check valve into the second main reservoir. The air in the second main reservoir is what is used to operate the locomotive's brakes. The check valve we just mentioned is there to ensure that we still have air in the second main reservoir to supply the brakes in the event of a separation happening causing the first main reservoirs to vent to atmosphere. To avoid excess accumulation of moisture and to prevent debris from getting into the air brake system, the reservoirs have associated automatic drain valves and blowdown filters. Alright, now we've got our compressed air and we've got it stored on the locomotive. So how do we use that compressed air to stop? Well, the simplest system to understand on a locomotive is the independent brake. The independent in independent brake refers to the fact that it will allow the brakes on the locomotive to both apply and release regardless of what the automatic brakes are doing. For now, we're just going to talk about the simplest form of independent application and release. To start out with that, we'll start with the SA26 independent brake valve. I'm going to shorten that to independent brake valve. I use a lot of words over and over again in this video enough. Anyway, the independent brake valve is located in the control stand and is what the engineer uses to apply or release the independent brakes on the locomotive. As simple as it would be to just use this valve to send air directly to the brake cylinders, we can't do that for a couple reasons. The first reason might be familiar to you if you've actually watched some of my previous videos, and that is that not all locomotives use the same brake cylinder pressure. To give an example, I work with locomotives that use 32 psi, 45 psi, and 72 psi depending on the brake rigging setup. The second problem we run into is response time. Brake cylinders on a locomotive, even more so if you have multiple locomotives in a consist, have a very large volume, and running all of that air through a single valve in the cab would cause the equipment to have a very slow response. Both of these problems can be solved by a common solution, namely the J-relay valve. There are several different types of J relays that are used, and they all have different names, but for now I'll just list off 4 common ones. J1 relay. These are used on locomotives equipped with class brake rigging and that use 2 cast iron shoes or low friction composition shoes per wheel. Full application pressure for locomotives with these relays is 45 psi. J14 relay. Used on locomotives equipped with clasp rigging and that have 2 composition shoes per wheel and 9-inch brake cylinders. Full application pressure on these locomotives is 45 psi as well. J1.616 relay. Used on locomotives equipped with single shoe rigging with 1 composition shoe per wheel and 9-inch brake cylinders. Full application pressure on locomotives with this relay is 72 psi. J46 or J46B relay. Used on locomotives with clasp rigging with 2 composition shoes per wheel and 10-inch brake cylinders. Full application pressure on locomotives with this relay is 32 psi. As a note, the B in J46B refers to the presence of an in-shot. If I could find a picture of one, I'll throw one up here. Anyway, now we've seen what a J relay looks like, let's get into how it actually fixes the 2 problems we just talked about. So the issue regarding the different locomotives having different brake cylinder pressures is solved by the different types of J relays. All the J relays we just mentioned can take the same signal pressure and will send a corresponding brake cylinder pressure that we just talked about. Some of them will step them up, some of them will step them down, some of them use the same pressure. It all depends on the locomotive, but all we have to do is send the same pressure to all of them and you will get the correct relative amount of pressure to the brake cylinders. The issue of slow equipment response is solved by the signal pressure only requiring a small volume of air compared to the locomotive's brake cylinders. As a matter of fact, part of why they're called a relay valve is because they work similar to an electrical relay. A small volume of air is used to control the larger volume of air that goes to the brake cylinders, much like how an electrical relay uses a small amount of current to control a larger amount of current. By using a small volume of air for the signal pressure, the independent brake valve in the cab only has to pass that small volume of air in order to get a full application on all the brake cylinders. Another noteworthy feature of the J relay valve is that it maintains against brake cylinder leakage. If the pressure in the brake cylinders drops below what the correct amount is based on the signal pressure, it'll automatically put more air into the brake cylinders to keep the pressure up. Alright, so let's recap our level 3. The independent brake on a locomotive allows the engineer to apply or release the brakes on the locomotives irrespective of what the automatic is doing. The independent is controlled by the SA26 independent brake valve in the control stand. The independent brake valve sends a signal pressure to the J relay valve on the locomotive, which will react to that signal pressure to send an appropriate pressure to the locomotive's brake cylinders. The J relay is also responsible for maintaining pressure in the brake cylinders against any leakage. Alright, the automatic brake. Probably one of the more misunderstood things about a train. If you know absolutely nothing about how automatic air brakes work, I actually recommend you check out another one of Hyce's videos. In this case, it's his Air Brakes 101 video. In this level, we're going to talk about how the automatic brakes work on a locomotive. Unlike with the independent brakes, we actually will not be starting with the automatic brake valve. That'll come up later. My reasoning for this is because the automatic brake valves on a locomotive don't really have much to do with the actual functioning of the automatic brakes. A locomotive that's not even running will still have automatic brakes that function. We'll talk more about that at the end of this video. Alright, so right off the bat, we'll get into what's probably the biggest misconception about how automatic brakes work. The automatic and automatic brake refers to the fact that in the event of some kind of failure, the brakes will automatically apply. The misconception comes in when people hear that and assume it works like the spring brakes on a semi or a tractor trailer. The confusion is understandable because most people are more familiar with a semi than a train. However, the automatic brake on a train does not work the same way as the spring brake on a semi. So let's get into a little bit more about how this works. This is specifically for locomotives. Freight cars are a different beast, and passenger cars are still a different beast. and I'm not a carman, so I won't go into how they work really in this video. Again, I recommend you check out Hyce's video if you're interested. So how exactly do the automatic brakes on a locomotive work? Well, the automatic application and release of the brakes is handled by the service portion of the 26F control valve. I'll just call it the control valve. So if you hear me say 26F or 26F control valve or just control valve, this is what I'm talking about. This valve is connected to the brake pipe through a branch pipe which contains a combined strainer and cutout cock assembly. This assembly is here to remove any foreign matter that has found its way into the brake pipe. The cutout cock can be used to prevent functioning of the automatic brakes on the locomotive, although I'm honestly not sure it's even legal to move a locomotive like that, but you can do it. Anyway, when the brake pipe is charged in order to release the automatic brakes, the control valve uses the pressure in the brake pipe to charge 3 reservoirs. However, we're only going to worry about 2 of them for now. The 2 that we're worried about are the auxiliary reservoir and the control reservoir. The auxiliary reservoir is a volume of air used by the control valve to send a signal pressure to the J relay valve. Yes, this is the same J relay we just talked about in the independent level. It'll react to a signal from the control valve just the same as it would from the independent brake valve. When the brake pipe is fully charged, the pressure in this reservoir will rise until it equals the pressure that's in the brake pipe. When a reduction is made in the brake pipe, a check valve keeps the pressure in this reservoir so that it can be used to send the signal pressure to the J relay. The control reservoir is a volume of air that the control valve uses to compare the pressure in the brake pipe to. So when the brake pipe is fully charged, the pressure in this reservoir will rise to the same pressure that's in the brake pipe. Again, when the pressure in the brake pipe drops, a check valve holds the pressure in this reservoir. The control valve will then compare the pressure in the control reservoir to the pressure in the brake pipe, and based on that difference, it will send a certain signal pressure from the auxiliary reservoir to the J relay valve. Then the J relay valve will apply the brake cylinders just like we talked about. If the brake pipe pressure is then returned to where it started, the pressure difference between the control reservoir and the brake pipe goes away, so it will vent the signal pressure to the J relay, and the J relay will then release the brakes. Everybody got all that? Let's try going through it again. The automatic air brakes on a train do not work like the spring brakes on a semi-truck. The automatic brakes on a locomotive are controlled by the service portion of the 26F control valve, which reacts to a change in brake pipe pressure to send a signal to the J relay valve. The control valve is connected to the brake pipe through a branch pipe and combined strainer and cutout cock assembly, and because it is only connected to the brake pipe, no input from the control stand is required for the automatic brakes to apply. When the brake pipe is fully charged, the control valve charges 2 reservoirs that it uses to send the signal pressure and to compare the brake pipe pressure to. When a reduction in brake pipe pressure occurs, the air in these reservoirs is used to send the signal to the J relay and apply the brakes. Now that's all great, but on locomotives we don't usually want to use their air brakes to slow down. We want to use the brakes on the train behind them. So in our next level we'll talk about something that doesn't seem to be horribly well known outside of the industry. Alright, now that we have some understanding of how the automatic brakes on a locomotive work, let's talk about another feature. Remember how I mentioned that the independent brake can be used to apply and release the brakes no matter what the automatic is trying to do? Let's elaborate on another part of that a little bit more. One of the functions of the SA26 independent brake valve is to allow for what is technically called independent release of an automatic application. Like I said, I'm going to use words a whole bunch of times in this video, but I'm definitely not saying that every time. In industry, we'll simply call this bailing off the brakes, or you'll hear me simply say bailing. So let's get into how we do that. In level 4, we talked about the service portion of the 26F control valve. Predictably, there's another portion of it, and that other portion is called the quick release portion. And this is what allows the engineer to bail his brakes off. In order to bail off the brakes on a locomotive, the engineer has to push down on the handle of the independent brake valve. When this happens, a signal is sent to the quick release portion of the control valve, and when this signal is received, 2 things happen. First, a valve is opened that vents the signal pressure going to the J relay, and second, a valve is open that allows the pressure in the control reservoir to vent to atmosphere. The combination of these effects causes the brakes on the locomotive to be released, and also, in a sense, resets the service portion of the control valve, since the control reservoir is now vented down to the same pressure that's in the brake pipe again. So when the engineer releases the handle, the control reservoir and the brake pipe are at the same pressure, so the service portion of the control valve doesn't immediately set the brakes up again. Hopefully that made some amount of sense, but to try and shorten it, when the engineer pushes down on the handle of the independent brake valve, a signal is sent to the quick release portion of the control valve. This signal causes the signal being sent to the J relay valve from the control valve to be released, and also causes the pressure in the control reservoir to be reset to whatever pressure is in the brake pipe. This releases the brakes on the locomotive and also prevents them from immediately reapplying when the engineer lets go of the independent handle. So now that we know how the automatic brakes react to the brake pipe pressure and how the engineer can independently release the locomotive's brakes, let's go over how we actually control the pressure in the brake pipe. Alright, we're halfway done. We just talked an awful lot about how the automatic brakes on a locomotive work, and we also learned that it doesn't require any input from the control stand to function. It just takes a change in brake pipe pressure. However, in order to run a train, we do still need some way or another to control the pressure in the brake pipe in order to actually run the automatic brakes on the train. So how do we do that? Well, that's what this level is about, but first I want to talk about the automatic brake valve itself. So here we go. 26L equipped locomotives use the 26C automatic brake valve, and that is how we control the pressure in the brake pipe. Predictably, I'm not going to say all that again, so I'll just call it the automatic brake valve. Before we get into how it works, I want to talk about the handle positions for the automatic brake valve. From left to right, they are as follows. Release. This position of the handle is used by the engineer to fully charge the brake pipe on his train and release the automatic brakes. Minimum reduction, or initial reduction. This position creates a roughly 5 psi reduction in brake pipe pressure. This is enough of a reduction to get the brakes on all cars on the train to start applying. Service. This position is really a sector between minimum reduction and full service. As the handle is moved from left to right through this zone, the reduction in brake pipe pressure increases. Suppression. This position of the automatic handle is used to suppress or recover from a penalty application. We'll talk about those in the next level. It also provides a full service brake pipe reduction. Handle off. This is the position used to condition the automatic brake valve handle on trailing locomotives. In this position, penalty applications are suppressed and the pressure in the equalizing reservoir is reduced to 0. This position is called handle off because you can actually remove the automatic brake valve handle in this position. And lastly, we have emergency. This position is used to initiate an emergency application from the control stand. It also is used to recover from an emergency application caused by something other than the control stand, i.e. if something breaks into somewhere and the train dumps, the engineer has to go to this position in order to recover his air. So now that we know what the positions are for the automatic brake valve handle, let's get into how it actually works and lets us run our train brakes. The first thing to understand about how the automatic brake valve works is that the engineer does not directly work with the air in the brake pipe. The brake pipe volume is inconsistent depending on how many cars are in the train. So instead, we use something called the equalizing reservoir, and the automatic brake valve itself will automatically handle the pressure in the brake pipe. Now, what exactly is this equalizing reservoir and how is it controlled? Well, that's what the rest of the level's about. The equalizing reservoir on a locomotive is a small volume of air which is used by the automatic brake valve to balance the pressure in the brake pipe against. Inside of the automatic brake valve there is a feed valve and a relay valve. With the handle in release and the automatic cut in, the feed valve will send air to the equalizing reservoir based on the setting made by the engineer. Typically it's 90 psi. The relay valve will then see that pressure and will put air from the main reservoir into the brake pipe until the pressure in the brake pipe and the pressure in the equalizing reservoir are equal. When the engineer moves the handle to somewhere in the service sector, pressure in the equalizing reservoir is vented to atmosphere until it reaches the pressure corresponding to the position of the handle. Since the automatic brake valve is self-lapping, the pressure venting is automatically stopped. Non-self-lapping brake equipment like number 6 and 24RL, which we'll mention later, require the engineer to manually stop the venting of the equalizing reservoir by moving the handle to a dedicated lap position. Self-lapping brake equipment like 26L does not have this feature, so it's a little bit easier to run. Anyway, when the relay valve sees the pressure decrease in the equalizing reservoir, it will vent air from the brake pipe to atmosphere until the pressure in the brake pipe is equal to the pressure in the equalizing reservoir again. Then when the engineer moves the handle back to release, the feed valve will raise the pressure in the equalizing reservoir back to where he started, and then the relay valve will see that and respond by raising the brake pipe pressure again. This will cause the automatic brakes on the entire train to release. Note that the relay valve simply just makes the pressure in the brake pipe and the pressure in the equalizing reservoir match, or at least does the best it can. This allows the automatic brake valve to automatically maintain brake pipe pressure against any kind of leakage in the train line. This is true no matter what position the handle is in. Alright, that was another good chunk of information, so let's try and summarize it. When cut in, a feed valve inside of the automatic brake valve will fill the equalizing reservoir to the pressure setting made by the engineer. Typically this is 90 psi. The relay valve, which is also inside the automatic brake valve, will then fill the brake pipe until the pressure in the brake pipe matches the pressure in the equalizing reservoir. When the engineer makes a reduction in brake pipe pressure, the equalizing reservoir is vented slowly to atmosphere, which causes the relay valve to also vent air in the brake pipe to atmosphere. When the engineer wants to release the automatic, he can move the handle back to release, which will cause the feed valve to refill the equalizing reservoir, and then the relay valve will refill the brake pipe. All the pressures returning to their initial starting point is what causes the automatic brakes to release on the entire train. The action of the relay valve to keep the pressure in the brake pipe equal to the pressure in the equalizing reservoir is what provides pressure maintaining for the brake pipe against any amount of leakage, no matter what position the automatic handle is in. Now, before we move on, I want you to bear in mind that the automatic brake valve actually has several other functions. We'll get into 2 of these in levels down the line, but we will not be going through all of them here. Alright, penalty applications. This is something else that's not terribly well known by people outside the industry, but they are a very important safety feature. A penalty application is an application of the automatic brakes on a train which is initiated by a system on board the locomotive that monitors for inputs from the engineer. If there's no input from the engineer for a significant amount of time, an alerter in the cab will start to flash and may even sound an alarm. If the alarm is not nullified soon enough, the system will trigger an application of the automatic brakes on the entire train. This is designed to prevent a train from running out of control in the event of an engineer passing out or something else crazy happening. So now that we know a little bit about what a penalty application is, let's get into how we actually achieve that. Well, the fun part of a penalty application has to do with the P2A, or formerly P2, penalty application valve. You'll hear me just say P2A for the rest of this video pretty much. Anyway, remember how we just talked about in our last level how the automatic brake valve uses the pressure in the equalizing reservoir to control the pressure in the brake pipe? So if we want to apply the brakes on the train, we have to get the pressure in that equalizing reservoir down somehow. So how do we do that when that's being controlled by the engineer through the automatic brake valve? Well, that's where the P2A comes in. The P2A is plumbed between the charging pipe from the automatic brake valve to the equalizing reservoir and the equalizing reservoir itself. It's controlled by 2 magnet valves, and before we move on, a magnet valve is simply a valve that can be opened or closed with an electrical signal. Anyway, the magnet valves we're talking about right now are the safety control and overspeed control magnet valves. Some locomotives only have them 1, some of them have 2. There's different arrangements because of course there are. Anyway, both of these magnet valves are normally energized and are such held closed. In the event of either an overspeed or a lack of input from the engineer, the corresponding magnet valve will open, which causes the P2A to initiate a penalty application. When one of the magnet valves drops out, the P2A will do 3 things. 1. It will cut off charging of the equalizing reservoir from the automatic brake valve. 2. It will connect the equalizing reservoir either to atmosphere or to another reservoir through a choke to provide a service rate of equalizing reservoir reduction. This will initiate an application of the automatic brakes on the entire train. 3. It will trip the PCS, pneumatic cutout switch. This is a pressure-operated switch which will stop the locomotive from loading and will also nullify any dynamic braking. On some locomotives, there's a pneumatic cutout switch and then a dynamic cutout switch. They both do the same thing. They're both tripped during a penalty application. Now, once a penalty application has been initiated, the engineer has to move the automatic brake valve handle to the suppression position that we talked about earlier. In this position, the automatic brake valve sends a signal to the P2A, which causes it to reset. Once the P2A is reset, the engineer can move his handle back to release, and the P2A will now allow recharging of the equalizing reservoir, and then the automatic will recharge the brake pipe. This will again cause the brakes to release just like it normally would. One last thing I want to mention about penalty applications is that a locomotive that is in trail has penalty applications suppressed, like we talked about. And if a locomotive has more than enough pressure in the brake cylinders, typically it's about 25 psi, this will also suppress a penalty application. This way a crew alerter isn't sitting there constantly going off whenever you're just sitting in a siding somewhere with the brakes set. In these situations, even if the magnet valves decide to drop out, the air system is physically prevented from actually causing a penalty application. Alright, so let's recap that a little bit. A penalty application occurs either when the engineer doesn't make any inputs at the control stand for a long time, or when a set speed limit is exceeded. When that happens, one of two magnet valves drop out, and that will cause the P2A to initiate a penalty application of the automatic brakes. During a penalty application, the equalizing reservoir is cut off from charging, and the pressure in it is slowly reduced to cause an application of the train's automatic brakes. The PCS on the locomotive is also tripped to cause a power knockdown and prevent the locomotive from loading. The engineer can recover from a penalty application by putting the handle of the automatic brake valve in the suppression position and holding it there until the P2A resets. Once the P2A is reset, the engineer can move the handle back to release to recover the air of his train. Note that penalty applications are prevented when the locomotive is in trail or has the brakes applied. Alright, now that we have an understanding of penalty applications, let's get into something that's a little bit more well known. There's a very high chance if you're watching this video that you know at least a little bit about emergency applications on trains. They are probably one of the most important safety features of the automatic train brakes and occur when the integrity of the brake pipe is lost. This causes the pressure in the brake pipe to rapidly drop and the brakes to slam on. We already talked about how the automatic brakes work, so let's get into what sets an emergency application apart from a normal service application. The first and biggest thing that sets an emergency application apart from a service application is the rate of brake pipe pressure reduction. During an emergency application, the brake pipe pressure drops rapidly. In fact, brake equipment on cars and many locomotives is designed to react to an emergency rate of reduction by actually venting the brake pipe pressure even faster. I won't talk about how cars accomplish that in this video, but we will talk about how locomotives do it. Locomotives are typically equipped with either one or two of these. This is a number 8 vent valve. These valves are connected to the brake pipe and respond to a rapid drop in pressure by opening to speed up that rate of pressure reduction. This is done to speed the propagation of the emergency application along the length of the train, since on a long enough train, the cars farthest from whatever started the emergency application may not actually go into emergency. Another thing that both cars and locomotives do during an emergency application is increase the pressure sent to the brake cylinders. Again, we're not talking about cars today, but on locomotives, this is actually controlled by the service portion of the control valve we already talked about. When the service portion of the control valve senses low enough brake pipe pressure, it allows a higher signal pressure to be sent to the J relay than it normally would. This will obviously increase brake pipe pressure. Now this is where we get into the extra functions that are needed on a locomotive during an emergency application. In addition to the two things we just talked about, locomotives have 3 other functions that they need to accomplish during an emergency application. And those functions are 1. To prevent locking of the wheels due to the increased brake cylinder pressure we just talked about, sand is applied to the rails for a certain time length after an emergency application. 2. A power knockdown, the same as what we just talked about during a penalty application, is also provided during an emergency application. 3. On the lead locomotive in a consist, we want to stop the automatic brake valve from charging the brake pipe. This is done to keep the lead locomotive from exhausting all of its main reservoir air trying to recharge the brake pipe during an emergency application. With the piping arrangement that I am familiar with, all three of these functions are provided by the A1 charging cutoff pilot valve. I'll be shortening that to A1 charging, so here we go. Starting with the first function we talked about, sanding, the A1 charging is plumbed into the brake pipe, and when the brake pipe is fully charged, pressure from the brake pipe is used to charge a small reservoir. When an emergency rate of brake pipe reduction occurs, air from this reservoir is sent to another pressure switch called the emergency sand switch, or ESS, and the pressure is slowly exhausted through a timing choke. When the ESS is closed by this air pressure, it sends a signal to the sanding magnet valves, which will blow sand at the rails. The pressure in this timing reservoir takes about 30 seconds to exhaust through the choke, and once the pressure is exhausted, the pressure switch opens and the sanding stops. So now for the next function, the power knockdown. Remember the PCS we just talked about in the last level? Well, the A1 charging can also send a signal to that PCS and cause a power knockdown. That's pretty much it. When an emergency rate of reduction is sensed and it goes to blow sand, it also sends a signal pressure to the PCS. Okay, now for another thing that's not terribly well known outside the industry, and this thing is actually the reason that the A1 charging cutoff pilot valve got its name. The automatic brake valve has a relay valve inside of it, and like we talked about earlier, that relay valve simply tries to keep pressure in the brake pipe at whatever the pressure in the equalizing reservoir is. However, if the emergency application is not initiated by the engineer from the control stand, the brake pipe pressure for some reason goes to 0. The relay valve is going to see that and will try and charge the brake pipe back up to 90 psi, or whatever pressure it started at. This is a problem because that means it's venting the main reservoir air, which is what we're relying on in order to stop, straight to atmosphere. The automatic brake valve also has another valve inside of it known as the brake pipe cutoff. The A1 charging can send a signal pressure to this cutoff valve in the event of an emergency application, and this is done to, predictably, cut off charging of the brake pipe. This keeps the locomotive from trying to exhaust all of its main reservoir air in order to recharge the brake pipe. So, on a lead locomotive, once the A1 charging has been tripped by an emergency application, the brake pipe can no longer be charged. So in order to recover the air of the train, the engineer has to reset the A1 charging. This is accomplished by putting the handle of the automatic brake valve in the emergency position. In addition to triggering an emergency application, this also sends a signal pressure to the A1 charging that will cause it to reset. Once the A1 charging resets, the pressure holding the brake pipe cutoff closed will be released, and the handle can then be returned to release, which will recharge the equalizing reservoir and the brake pipe. Note that on a trailing locomotive, the A1 charging will automatically reset itself after the 30 seconds of sanding is up. So let's try and recap all that. Emergency applications are characterized by a rapid drop in brake pipe pressure, which is often accelerated by venting, increased pressure to the brake cylinders, application of sand to the rails, a power knockdown, and the cutoff of brake pipe charging on the lead locomotive. The venting is provided by the number 8 vent valves, which open when a rapid drop in brake pipe pressure is sensed. The increased brake cylinder pressure is provided by the service portion of the 26F control valve we talked about. Sanding is controlled by a pressure switch, which is in turn controlled by the A1 charging cutoff pilot valve. This valve is also responsible for piloting the brake pipe cutoff in the event of a break-in-2. And if the application was not started from the control stand, i.e. a break-in-2, the engineer has to move the handle of the automatic brake valve to the emergency position and hold it there until the A1 charging has reset and he can then recover the air of his train. So now that we've got a pretty good overview of emergency applications, for our next level we'll talk a little bit about how the air brakes interact with the other type of brakes we have on locomotives, namely the dynamic brakes. Alright, so now we've got a pretty good handle about how the air brakes on a locomotive work. Let's talk a little bit about how the air brakes and the dynamic brakes interact with each other. This should be relatively short, but I did want to make sure we've been over everything else in order for this to actually start to make a little bit of sense. For those not familiar with what dynamic braking is, it's kind of analogous to a jake brake on a semi or engine braking in your car. During dynamic braking, the connections to the traction motors are altered to turn them from motors into generators, and by applying a resistive load to those traction motors in that state, we can slow the train down without having to use the air brakes. However, sometimes dynamic braking on its own isn't enough, and other times the engineer will use the automatic brakes and the dynamic brakes at the same time for train handling. It gets complicated fast, and I'm not an engineer, so I don't really get that much into it. However, we do not want to have both our air brakes and dynamic brakes working very hard at the same time due to adhesion concerns. Basically, we don't want to slide wheels. So to prevent these issues, we have two other components that we haven't mentioned yet, namely the independent pressure switch, or IPS, and the dynamic brake interlock, or DBI. The former is a pressure switch on locomotives that are equipped with extended range dynamic braking. We won't get into extended range dynamic braking and what it is, but the IPS is there to prevent the dynamic brakes from operating in extended range when the independent brake valve is applied. The DBI is a magnet valve that is present on locomotives with dynamic brakes, usually, and can be set up in two main configurations. One is between the service portion of the 26F control valve and the J relay. In this arrangement, when the locomotive goes into dynamic braking, the DBI is energized, which opens and vents the signal being sent to the J relay. This prevents any automatic application of the locomotive's brake cylinders, and if the brake cylinders were already applied, the DBI will cause them to be released. The second arrangement of the DBI has it supplied by main reservoir air and then delivers that air to the quick release portion of the 26F control valve. This causes the brakes to actually be bailed off in the same way as if the engineer had done so with the independent brake valve. The way you can tell the difference with these is whenever you check the DBI, if you move the handle back to setup, if the brake cylinders come back on, you have the first arrangement we talked about. If they do not, you have the second one. A little tangent I'll mention here is positive train control. For reasons I'm not really sure of, PTC does not play well with the DBI. It's something to do with a safety concern, with penalty applications and being in dynamics, but I really don't know enough about this to tell you with confidence why it is a thing. But on a locomotive that is equipped with positive train control, you will not find a DBI that works. Alright, now we've got a pretty good handle on basically everything on how an individual locomotive works. So let's get into what happens when we start connecting multiple locomotives together. Brace yourselves, because this gets fun. Alright, again, I'm sure if you're watching this video, you've seen multiple locomotives connected together to pull a train. How exactly does that work? You know there's only one engineer, so how does the one guy in one cab control all of those locomotives? I mean, obviously we're going to be skipping the electrical portions of this, but how does the air know what's going on? There are a few components we have either yet to talk about or that we need to add a little bit more to that we talked about earlier, and those are, first, the MU or multiple unit hoses, second, the MU2A valve or double heading cock, and third, the cutoff pilot valve, which is not the same as the A1 charging cutoff pilot valve, because, you know, that would be too simple. Anyway, firstly we have the MU hoses. These are 3 hoses in addition to the brake pipe hose that are strung between locomotives in a consist. From the center to the outside, the hoses are the main reservoir hose, the actuating hose, and the independent application and release hose, or the independent equalizing hose, brake cylinder equalizing hose, brake cylinder hose. There's a bunch of different names. We'll get into that later. The first hose, the main reservoir hose, we actually talked about all the way back in level 2. This hose connects all the first main reservoirs on every locomotive in the consist together. This allows all of the locomotive's air compressors to supply air to the train's brake pipe through the lead locomotive. This saves wear on the air compressor of the lead locomotive and allows for better response of the train's air brakes. The second hose is the actuating hose. This hose is connected to the actuating pipe that goes from the independent brake valve to the quick release portion of the 26F control valve. If that didn't give it away, the actuating pipe controls the bailing off of the brakes that we talked about way back in level 5. The final hose is the independent application and release hose. Again, we won't get too crazy into the IAR versus equalizing. That's later. This hose is connected to the independent application and release pipe on the locomotive. That pipe connects the independent brake valve and the J relay. Depending on the piping arrangement of the locomotive, this usually just takes the signal pressure from the independent brake valve and sends it to the J relay. So this hose allows one independent brake valve to send that signal pressure to all the J relays in a consist. And then the J relay will respond to that signal pressure to give each locomotive the right amount of brake cylinder pressure. Alright, now we know what the MU hoses connect to and how they allow the needed signals to travel from locomotive to locomotive and how they allow one engineer to control all the locomotives from one control stand. However, the astute among you will notice that we still have a bit of a problem. Even though one control stand is actually controlling things, the other control stands are still there and they're still connected to those signal lines. So how do we keep them from messing with us? Well, that involves the other two things we talked about at the beginning, the MU2A, or double heading cock, and the cutoff pilot valve. We'll go over the cutoff pilot valve first, as it's the easier one to explain since we already talked about the brake pipe cutoff earlier. Remember that the automatic brake valve has a valve inside of it that cuts off charging in the brake pipe. Back in level 8, we learned that this is used to prevent the lead locomotive from trying to recharge the brake pipe in the event of a break-in 2. Now, the other way it gets used is specifically to cut out the automatic brake valve on trailing locomotives. Simply put, when the cutoff pilot valve is put in the out position, the brake pipe cutoff is closed, which prevents the automatic brake valve on that locomotive from trying to charge or vent air from the brake pipe. Now for the last and arguably most complicated part of this, the MU2A. Fortunately, we won't be having to go into insane detail, but there's a good bit of information to include here, because of course there is. In certain piping arrangements, the MU2A on a locomotive can simply be replaced with a double heading cock, which, by the way, a double heading cock is simply two hand-operated valves that share a handle. That's it. The two valves in the double heading cock are piped between the independent brake valve and the actuating and independent application and release pipes. On leading locomotives, these are left open to allow the signals from the independent brake valve to reach the MU hoses. When in trail, these valves are closed to prevent the independent brake valves on trailing locomotives from messing with the signals we're trying to send from the lead locomotive. Okay, so that's the basic idea behind MU control. However, for that explanation, we assume that we're dealing with other 26L equipped locomotives. Problem is, not every locomotive out there has 26L on it. Brace yourselves, because this is about to get messy. So in addition to being able to MU with other 26L equipped locomotives, some 26L equipped locomotives are also able to be MU'd to locomotives with, I'm pretty sure I have this right, 6BL or 6SL brake equipment. There's different types of brake equipment that are all number 6 or the equivalent of number 6 heavy iron. Please bail me out here. You probably know this better than I do. Anyway, you can get different types of number 6 brake equipment as well as 24RL brake equipment. And this is where the confusing part about the MU2A comes in. And because, of course, it can't even be that simple, there are different types of MU2As, specifically a 2-position and a 3-position version. The 2-position one is simply used, like we talked about before, as a double heading cock to close or open the lines between the MU hoses and the independent brake valve. However, the 3-position version of the MU2A can also be used on locomotives that are set up for what is called universal multiple unit control. In addition to the MU2A, locomotives with universal multiple unit control have an F1 selector valve. Hopefully I can find a picture of that somewhere to throw up for you guys. But the MU2A sends different signals to the F1 selector valve in order to pilot it for the operation with different types of brake equipment. This is an example of a 3-position MU2A valve. Note the 3 different positions on the escutcheon plate there. I'll mention that different MU2A valves, again, it couldn't be that simple, have different lettering on their plates. But anyway, I'm going to ignore the numbers on them and simply refer to the positions as lead or dead, trail 1 line, and trail 2 line. Firstly, lead or dead is predictably used when the locomotive is either the leader of a consist or is being towed dead in a train, i.e. the engine can't run or something similar to that. 1-line trail is used when a 26L equipped locomotive is to be trailed behind a locomotive that does not have an actuating line. Many locomotives with number 6 brake equipment don't have an actuating line. They only have an equalizing line, which is actually different to the independent application release pipe we just talked about. As such, a locomotive that requires an actuating line cannot be trailed behind a locomotive set up for single-line trail. The F1 selector valve allows a locomotive equipped with 26L brakes to actually be used behind a locomotive that's set up for 1-line trail. 2-line trail is used when a 26L equipped locomotive is to be trailed behind a locomotive that has both an equalizing and an actuating line available. Locomotives equipped with 24RL brake equipment, as well as locomotives equipped with 26L brake equipment, will pretty much always have both an equalizing and actuating line available. There is also a version of number 6 brake equipment, which I believe is 6BLC, that also has an actuating line, which allows it to be used in a consist with locomotives that require 2-line trail. Are you confused yet? Me too. Luckily, it gets even better when we get into the way this actually works. So, 24RL equipment requires an actuating line on the leading locomotive in order to work at all. That means that any 26L equipped locomotive can operate with any 24RL equipped locomotive in any combination, since both of these types of brake equipment always have an actuating line. Now, most arrangements of number 6 equipment do not have an actuating line. Again, the exception is, I think, 6BLC. For all other arrangements of number 6 equipment, they cannot be used in lead ahead of a locomotive either with 24RL brake equipment or 26L brake equipment that is not set up for universal MU control. However, a 26L equipped locomotive that is set up for universal MU control can be used with any number 6 equipped locomotive, as long as it's actually set up for MU hoses, in any combination. Note that even if a 26L equipped locomotive is leading, a number 6 equipped locomotive cannot be used between a 26L or 24RL and another 24RL equipped locomotive, or a 26L equipped locomotive that's not set up for universal MU control. To try and boil that whole mess down into something relatively simple, if the locomotive has an actuating line, it can be used in any combination with any other locomotive that has an actuating line. If the locomotive does not have an actuating line, it can only be used in combination with another locomotive with no actuating line or a 26L equipped locomotive that is set up for universal MU control. However, a locomotive with no actuating line can be used on the tail end of a consist that does have an actuating line, but it cannot be used in the middle between locomotives that need an actuating line. I really hope that made some kind of sense. I know I kind of went down a rabbit hole, and I'm willing to bet that I screwed something up. However, even with all that, we're still not done. We have to talk about dead locomotives and setting the control stand up in what is called a boxcar. Technically speaking, a dead locomotive can have its engine running, but what really makes it dead is usually that the air compressor doesn't work. Since older EMDs have a compressor that is driven by the engine, like we talked about, if the air compressor goes kaboom, the engine will not be running. So without an air compressor, it can't supply itself with air in order for the brakes to work. So it needs to be able to receive air from some kind of external source. And this is where something called the dead engine fixture comes into play. For those of you that know a bit about how brakes on freight cars work, this will sound somewhat familiar. The cars charge an onboard reservoir from air in the brake pipe, and the dead engine fixture allows a locomotive to do the same thing. It connects the brake pipe to the second main reservoir. The check valve will hold the air in the second main reservoir, and the dead engine fixture allows charging of it. Once the air is in the second main reservoir, the locomotive now has air that it can actually operate its brakes with, which on a dead locomotive is handled by the control valve like we talked about earlier. However, just opening the dead engine fixture isn't enough on its own. We also have to set up the control stand properly. In addition to the lead and trail setups we touched on earlier, there is also a setting called boxcar. With the control stand in boxcar, the automatic brake valve is put in handle off with the cutout pilot valve in out, just like it is on a trailing locomotive. Meanwhile, the independent brake valve is put in full release and the MU2A is left in lead or dead position. The reason the MU2A is left cut in is to prevent any issues caused by buildup of air pressure in the actuating and or independent application and release pipes. With the MU2A cut in, any pressure that builds up in these pipes will be released by the independent brake valve. So in order to put a locomotive into boxcar, you have to put the automatic and handle off, put the charging cutoff pilot valve in out, put the independent in full release, and leave the MU2A or double heading cock cut in. In this position, the brakes on a locomotive will apply and release in response to the automatic brakes on the train, just like any freight car would. One thing I do want to mention about this setup is the dead engine fixture doesn't necessarily have to be open in order for the brakes to work like it's in boxcar. A locomotive that's fully functional can be put in boxcar with the dead engine fixture closed because the air compressor is still working, and it just saves you time having to lace up MU hoses. Alright, that was a lot of information, and hopefully most of it sank in. So let's try and very briefly go over what we talked about. So first, we talked about the air compressor, how it's driven by the engine and unloads itself because it's always turning. We talked about the fact that we need somewhere to keep the air, so we have main reservoirs, and we want to release moisture from it, so they have filters and automatic drain valves. We talked about how the independent brake valve doesn't actually send air to the brake cylinders, it sends it through a J relay valve, and this allows MU control and also allows for better equipment response. We learned about how the automatic brakes on a locomotive work and that it doesn't have anything to do with the control stand. We learned about independent release of automatic applications of the brakes, i.e. bailing the brakes off. We learned about the equalizing reservoir and how the automatic brake valve is actually mainly about controlling the equalizing reservoir to control the automatic brakes on the train. We learned about penalty applications and how we use these to automatically apply the brakes on a train in the event of the engineer falling asleep at the control stand. We learned about an emergency application and how we get sanding and venting and what sets it apart from a normal application of the automatic brakes. We learned about the DBI and the IPS, which are how the dynamic brakes can interact with the air brakes a little bit. And lastly, we went down a bit of a rabbit hole talking about MU control for different locomotives, what you can use with what and what you can't do, and how all that works. So hopefully you guys are still awake after all of that, because now we're going to go climb on an actual locomotive and look at what these parts look like in context, and then we'll go through an air test and you guys can get out of here. Alright guys, so here we are talking about our air system, and I figured what better way to start this off than by talking about the air compressor, which is what we're looking at here. You can see we have two big cylinders on the bottom and a small one on top. The two big ones are the low pressure jugs, the small one is the high pressure jugs, or the high pressure jug, excuse me. Hopefully you can hear me alright. Low pressure jugs suck air in from this air filler, compress it, feed it to the intercooler, which is located here on the back.
The intercooler, it goes into the high pressure jug, which will compress it up to main reservoir pressure, discharge it through this line, which runs over and down through the floor, and then goes through the radiator piping into our main reservoirs. This, and this are all unloaders. If we look down there, you can see the flange for the drive shaft, which runs under that shield right there, up that way to the front of the engine's crankshaft. Since any time the engine is running, the air compressor is turning, we need a way to keep it from building excessive air pressure. So there's a magnet valve that whenever the main reservoir pressure reaches a target, will send air down that line, which will push all of those unloaders down, and that holds the intake valve open on that cylinder, so the cylinder will push or will pull air in and then push it back out. It doesn't actually compress anything. So yeah, that's a little short snippet of what the air compressor is and how it works. There's obviously more detail, but for now I'm going to pause the recording and we're going to move on. Alright, now we're down on the ground. So now the air has come out of our air compressor, which is up there somewhere. Comes down, it goes through a radiator piping on the other side, comes back, and we'll jump across through that pipe right there, run all the way down to this end of the main reservoir, and go in. This is our first main reservoir. We are on the conductor side of the locomotive. One thing I don't think I mentioned before that I will actually mention here, you can see this hole right here. They are spaced relatively evenly around these main reservoirs. These are welded steel main reservoirs, and they are designed, these holes are designed so that if corrosion eats away at the inside of this, it'll start blowing air out of these holes before the main reservoir fails. So they are basically a telltale before the main res explodes and hurts somebody, or even worse, leaves you with no air to stop a train. These holes will give you a telltale. If we come down here to the other end of it, we have the automatic drain valve. This style of automatic drain valve is operated when the compressor cuts in or out. So each time the compressor cuts in, you'll get psh, psh. It'll get one cut or one blast when the compressor cuts in, then another one when it cuts out. You can see this little threaded piece right here. You want that to be all the way out. That means the valve is in automatic position. You can turn this. I'm not going to do it because it'll be loud because there's still air on this locomotive. But if you run it so that that threaded insert goes all the way in, it shuts it off and it will not cycle at all. Also, while we're over here, we have this. This is a J1 safety set for 150 psi. The pressure in the main reservoir reaches 150 psi. This valve will open to vent that to atmosphere, which prevents excessive accumulation of pressure inside the main reservoir. I'm going to pause the recording. We'll jump over and look at the second main res. Alright, here we are back on the engineer side of the locomotive, and here we have the second main reservoir. It looks remarkably similar to the first one. We even have the same drilled holes all the way through it. And if you look up here, this is the radiator piping. So it starts down there, comes up, runs back down, jumps over to the other side of the locomotive, comes back up, then runs into the first main res. That long stretch gives it the time to cool and for some of the moisture to start condensing out. You can see if I walk back down here, the second main res also has an automatic drain valve. Again, this one is timed to cycle whenever the compressor cycles. And then if we come back up here to the front, we have, these two pipes right here. This one, if we follow it back down there, tees off from where the air from the first main res comes over into the second main res. So this line is first main reservoir air. You can see this one right here comes out of the second main res. And from there we reach these two blowdown filters. These are to remove any water, particles, anything that gets into the air system that you don't want. The smaller one here, and you can see this one has a blow down, or a timed blow down that vents out of right there. So does this one, and that one vents from back there. This is a magnet valve, which we're going to learn about in a little bit actually. But that is what these filters are. This small one is for the first main res, so air that goes for the horn, bell, wipers, sanders, that kind of stuff will go through this. And this is from the second main res, so any air that goes through the brake system will run through this filter, then goes up into the control stand. Forgive my crappy camera work there. Also forgive me for coughing a bunch. Now, this right here is a number 8 vent valve. There's one on this side, and this valve will react to a rapid drop in brake pipe pressure, which is what is in this line right here. This is the brake pipe. The pressure drops. This valve will react to that, and it will open and vent that pressure out this line. The purpose of this is whenever you have something, a separation happen, you want to get the air out of that brake pipe as fast as you can so that the brakes on the entire train set up as fast as possible. So these vent valves help in propagating that emergency reduction faster. I'll go look and see if I can find the one on the other side. Alright, hopefully you guys can hear me over the air hissing. But now we have graduated from the components on the ground to the components under the cab. This is where most of your valves are, is underneath the cab floor on the engineer side of the locomotive. We'll start up here in the corner. These three components here are pressure switches. One of them will be your PCS, or pneumatic cutout switch. One of them will be the ESS, or emergency sand switch. And the third one will be, let me check. Yes, this locomotive does have dynamic brakes, or it does have extended range dynamic brakes. So one of them will be the IPS. This right here is your 26F control valve. This is the service portion. Quick release portion is right back there. You can see they both mount to the same pipe bracket. And then associated with them we have this right here. This is the combined strainer and cutout cock. There's a filter behind here. You take these 4 bolts off, pull the filter out, clean it, put it back in, and this cutout cock right here goes down into your brake pipe. So that allows the brake pipe pressure up into the control valve, and this valve will react to whatever that brake pipe pressure does to determine how much it needs to send to the brake cylinders. Actually, it doesn't go directly to the brake cylinders, but we'll get into that here pretty quick. Right down here, this makes up your dead engine fixture on this locomotive. This basically is a pressure regulator, and it also acts as kind of a one-way check valve type thing. And this right here is a cutout, so if the engine is live, it is wired shut and everything, and if you move that, you have to tag the isolation switch and all kinds of fun stuff. But this is a dead engine fixture. On some of them it's bigger and it's a separate piece that actually bolts onto it, but a lot of them are just like this. We look, let me get my flashlight out. Hopefully you guys will actually be able to see this. You can see we have reservoirs all over the place up in here, and there's 2 back there. You can see that one and that one. Now right here, this is a magnet valve. This one does not appear to be labeled, but there's one here, and one here. Most likely we have one of these is going to be a DBI, one of them is going to be your penalty magnet valve, and the third one is going to be an overspeed magnet valve. But these are what magnet valves looks like. You can see they have wires going into them and then some air plumbing. And also they look like these down here that we just saw a little bit ago. Right here we have our A1 charging. That provides the break-in 2 protection for this locomotive. One of those little reservoirs is plumbed into it, so when you release and charge your brake pipe, it sends air into that reservoir, and during an emergency application, it will release that air very slowly, and when it does, it will trip one of your pressure switches, your emergency sand switch. That'll start applying sand to the rail. And also, the full name for that is A1 Charging Cutoff Pilot. The charging cutoff is inside the automatic brake valve in the cab. So the other thing that this does, in addition to the sanding, is it sends air up to that charging cutoff, or that charging cutoff in the automatic, and that prevents the locomotive from trying to charge the brake pipe, because in the event of a break-in 2, it's now open to atmosphere. So that's a very important, I've actually seen on purpose to get air out of a locomotive. If you open an angle cock to atmosphere and put the automatic in release, if you don't dump it, but there's a way you can do that. I've seen a locomotive vent both main reservoirs in under a minute. It can happen very fast. Right here, we have the P2A penalty application valve. This valve will react to whatever magnet valve it is, but the penalty or overspeed magnet valve will cause that valve to trip, and that will open your equalizing res very slowly to atmosphere at a controlled rate. So it gives you a full service or even farther, depending on the locomotive. This one would actually go all the way to 0 if you let it go long enough. But that P2A is what gives you your penalty brake applications. Speaking of brake applications, we next move on to the J relay valve. This one is a J1.616, you can see, because it says it on it. Also looks like it's missing a bolt. That's interesting. I have to get that fixed before this goes anywhere. But this valve reacts to a signal pressure. That signal pressure can come from 2 places. It can either come from your 26F, if it's an automatic application, or it can come from the SA26 that's up in the cab if you're doing an independent application. Oh, and speaking of the SA26, the 26F quick release portion, what that is responsible for, I forgot to mention it earlier. When you bail with your independent, that vents the air. It does a couple things, but the short answer is the air that gets released comes out of this quick release portion, and that releases the brakes, and the brakes that releases the air from the brake cylinders on the locomotive. So yeah, that's actually, I think that's all of our stuff underneath the cab floor. So we'll go look at the stuff up in the cab real quick, and then we'll go do an air test. Alright, so now here we are in the cab. We are at the control stand. Right here, what we have is the 26C automatic. This controls the pressure in the equalizing reservoir, and by proxy the automatic brakes on the entire train. So right here is the charging cutoff pilot, which is part of it, that decides whether we are cut out, set up for freight operation, or set up for passenger operation. There is a difference. I'll get into that and from the rails up. I don't need to worry about that now. Right below that, we have the SA26 independent brake valve. This controls the brakes on just the locomotive in the consist. And if we go down here, this is a double heading cock. Some locomotives have an MU2A here. And you can see this one says closed and excuse me. You can see this one says closed, and behind this, you can't quite see it, but it says open in lead or dead. So while we're sitting here, I'll show you guys how to put a locomotive through a lead and trail. Right now, we are set up in lead, and the mnemonic I was always taught for how to do this was handle, handle, valve, valve. So what we're going to do is take the automatic to handle off which I haven't taught you guys the automatic positions yet, but, well, actually, yeah, let's just do that right now. So, we have release, we have initial reduction, we have the service sector, which goes from just past initial reduction all the way over. You don't quite get to the next bump. If you get all the way over, you'll actually feel a cam inside here hit. Again, we'll talk more about that later. This is full service. If we go past full service, we get to suppression. This position is how you recover from a penalty brake application. You have to move your automatic to suppression. You can either prevent it or it will let you recover from it. If we go past suppression, hopefully you can still hear me, the next position we get to is called handle off. Why is it called handle off? Ooh, this one's tight. This is why it's called handle off, because you can pull the handle off. Big surprise. This is the position you want your automatic to be in on a trailing locomotive in a consist. And then the last one we have is, and let me give it a couple seconds here. I think I can do this now without making a lot of noise. And the last position on the automatic brake valve handle is emergency. You can hear it's making a lot of noise because we're in lead, but this will open a big hole in the brake pipe straight to atmosphere. That's why it's sometimes called big holing a train. Again, you can hear we're making a lot of noise, so I'll pull it back to handle off so it shuts up and you can hear me. But that was emergency. If you do that with air in the brake pipe, which I didn't have right now, that makes a very loud noise and it is a big mess. So that's your automatic positions. Okay, now okay, I think everything's relaxed. Okay, now we'll talk about putting a locomotive in lead or trail. The mnemonic I was always taught is handle, handle, valve, valve. So what you're going to do is take your automatic handle, put it in handle off, which we just talked about. You're going to take your independent handle and put it in release. You're going to take your MU2A or double heading cock and put it in trail. Then you're going to take your charging cutoff pilot valve and put it in out. So what that'll look like in practice is handle, handle, valve, valve. This locomotive is now set up for trail operation. It will vent all the air out of the equalizing reservoir. It won't affect the brake pipe because we're in trail now, and there should still be plenty of air set on the brake cylinders. So this is in trail. To go back to lead, the same mnemonic works. You're going to go handle to release, handle fully applied, valve cut in, valve cut in. Now it's very important when you do this that you need to watch your equalizing reservoir compared to your brake pipe. You do not want to cut your automatic back in if the equalizing res is more than about 15 or 20 psi below the pressure in your brake pipe. You can see right now we got pretty much full service, about 66 give or take psi. So we need to make sure we have more than that in our equalizing res before we cut this in. So again, we'll go handle, handle, valve. We want to make sure we're back up above our brake pipe, and we are, so we can cut it in. You can see we're running out of air because the engine isn't running. But that gets us cut back in, and now we are back in lead. One component, I almost forgot to mention the air gauges. These are both duplex gauges. You can see we have two gauges, or two needles rather, on each gauge. These ones are actually conveniently labeled, But for ones that aren't, on the left gauge, the red needle in the back shows you the pressure in the main reservoir on the locomotive. The white needle shows you the pressure in the equalizing reservoir. On the right gauge, the red needle shows you the pressure in your brake cylinders, and the white needle shows you pressure in your brake pipe. If you're cut in and in lead, the equalizing reservoir and the brake pipe should always be the same. If you're in trail or in emergency or something weird happened, they can be different. But for the most part, these should be the same. This is how the engineer controls the brakes on his train. You can also see this locomotive, since it has a J1.616, actually has it labeled here, maximum independent brake cylinder pressure 72 psi. We are a tiny bit high, but that could be because of the gauge being off or a number of things. Could be that the automatic application compounded a little bit and it went a little high. There's a number of things that could have caused that. But that is our little spiel about all the components, and I also talked to you about lead and trail and the automatic handle positions. I'm going to stop this video, go do another one, and I'll show you how we do an air test. I'm going to have to actually start the locomotive for that. Alright everybody, here we are in the cab of a different locomotive because I screwed up the air test the first time I tried to record it. So we're going to try this again, and hopefully I don't biff it this time. Any consist that's going to leave needs to have an air test performed on it. And before you start that air test, the first thing you want to do is make sure that you have a handbrake set. In this specific case, this locomotive is secured by wheel chocks and a chain, so it doesn't really need a handbrake, but that's besides the point. You want to set a handbrake. The second thing you want to do is verify that you are in lead. You can see we are in release, cut in, you have the independence set, and we have our double heading cock in lead. Now with that, the next thing you want to do is you want to fully charge the brake pipe. Sorry. So to fully charge the brake pipe, you want to charge everything up to 90 psi. This process can take 3 to 5 minutes, but since this locomotive has been sitting for a while, we don't need to really worry about that. So the next thing we are going to want to do is release our independent. With the independent brake fully released, next step is to take a minimum reduction. You can see our brakes start coming on. We're going to increase that to a 10 psi reduction. And at that point you want to, there goes the alerter. At that point, you want to have your ground person verify that the brakes on the entire consist have applied. Once you've verified that those have applied, you are going to press down on the independent handle, like so, and verify that the brakes on the locomotives all release. Let me see here. Now, a feature I like to check is split reduction. So from here we are going to take our reduction up to a 20 psi reduction. When that happens, your brake cylinders should come back up. In this case we did, so we're good. Now also, whenever you do this, you want to make a note of where your automatic handle is. We're at a 20-pound reduction right now, so then later, whenever we come back to make a 20-pound reduction, we need to know where our handle's at. So from here, we are good. We can release our automatic. Everything should release. Now we're going to check to make sure our independent works right. So we are going to apply our independent. And release it. Now we're going to check how fast our equalizing reservoir pressure drops. So remember just a second ago I told you to remember where your automatic handle's at. So what we're going to do here
is we're going to take a 20-pound reduction all in one shot and time how long it takes that pressure to drop. And the crew alert is going to start yelling at me. Okay, so here we go. 1, 2, 3, 4, 5. That'll work. Say it's supposed to be between 3.5 and 6 seconds. In this case, we are good. Now, while we are here, I am going to go and check. Let me see if I can find a way to set this up. Not really. Okay. Yeah, I'm going to pause the recording and I'm going to come right back. Okay, sorry about that. So what I've done now is I have created a leak in the brake pipe. All I did was simply crack an angle cock open. This is how we check our maintaining feature. Whenever you do this, the pressure in the brake pipe should remain constant. In this case, you can see it is. It's not dropping off. So our maintaining feature is working. I'm going to pause the recording again and go close that leak. Okay, now we've closed our leak off. Another feature we want to check while we're here is our DBI. In order to verify that, you need to have your reverser in and thrown. Give me a second. Make sure we're in run. You got your reverser in and thrown. Take your dynamic brake handle, move it to setup. Let the switched gear do its thing, and then as soon as you move it into position, the pressure in the brake cylinder should release. This is called your DBI, or dynamic brake interlock. That feature is designed so that whenever you take a reduction on the train brake, you don't get brakes on the brake cylinders while you're using your dynamic brakes. It's basically a kind of anti-compounding feature. So we're going to move this back to setup. You can see they come back up. I've seen a couple locomotives that won't do that. It probably depends on the piping arrangement, but a lot of them, whenever you go back out, your brake cylinder pressure comes back on. It's not the same as bailing off. I'll also mention while we're talking about this, if you have a locomotive that's equipped with PTC, they do not have DBIs on them. For reasons I'm not entirely sure of, PTC and the DBI do not play nice. So on PTC equipped locomotives, the engineer just has to manually bail the brakes off. So, go back to off, and while we're here, we are going to check our automatic cutout. To do that, we're going to cut our automatic out. Now you can go back to release. You can see our equalizing reservoir pressure came up. Our brake pipe did not move. That is good. That is what you want. That means that our automatic is not sending any air into or out of the brake pipe. You can see now if I cut this back in, the brake pipe comes back up. And our brake cylinders also release. Okay, now the next thing we're going to do here is we are going to verify our crew alerter operation. Now that we have all the brakes released, it's going to do that. So it should nullify on a few things, one being the manual reset, another one being the horn, some of these take forever. That one's good. Some locomotives, although I highly doubt this one has it, some locomotives will nullify on the crossing bell. We'll see if this one has that feature. It does not. So we'll move the throttle. And it nullifies. Next one we'll check is the dynamic brake handle. This one does not, so we'll hit the reset again. Now the next thing it should nullify on is if you apply the independent or the automatic and get about 25 psi of air pressure in your brake cylinders. So when it starts cycling again, we'll apply the independent. Get up to about 25 psi, it'll shut up. Next we'll use the automatic. Maybe. If it ever gets enough air in it. There it goes. So, should do that. Another thing it should nullify on is if you bail with your independent. Bail off and it nullifies, so our crew alerter is good. I've also seen some alerters that'll nullify on, actually yeah, we'll check that one. I've seen some alerters that'll nullify on sand, so we'll try that real quick. That one does not, so we're just going to let it dump. Okay, we are now in what we call a penalty application. You can see we have a PCS open light. We can see our equalizing res pressure is dropping. On this locomotive, it'll drop all the way to 0. Also note that we do not have any throttle response while your PCS is open. If you don't have any throttle, you won't have any dynamic braking either. And if we were loading, it would knock the load off, all kinds of stuff. It's basically a dead man feature. If you fall asleep at the control stand, we want things to stop. We don't want them to take off out of control. So now that we're here in penalty, the way you're going to recover from it, you're going to take your automatic and move it to suppression. You will wait. Usually this PCS light will go out. There, see the PCS light went out. So now if we go back to release, we can recover the air on our train. And now the brakes are going to release again. And one thing I will mention here that I've heard about is, I think it was Heavy Iron that brought this up. There's an old myth about these old EMDs that if you had them in notch 5, which we'll put ours in here. But there's a myth about these old EMDs that if they're in notch 5 and the alerter dumps, that it'll shut the engine down. Based on my understanding and me spending some time looking at prints, they should not shut the engine down. However, the throttle MU stop should still work even with the locomotive in PCS. We're going to let it dump here and we'll see what happens. There you go. You can hear we went right back to idle. And I'm gonna check and see. I'm not gonna actually shut the engine all the way down, but you'll hear it start to. We pull off. You can see our MU stop still works. So we are going to come over here and recover our air. Wait on our PCS light to go out. Now we've got our air recovered. Alright, so that was a little bit of a tangent. The last thing we're going to check here is I'm going to show you guys how to perform a brake pipe leakage test. This is the last part of your air test. So what you're going to do here is you're going to make a 20 psi reduction. Right there's 20 pounds. Let pressure stabilize for a second or two. Then you're going to take your automatic and cut it out. And you are going to start counting brake pipe leakage. Let me set the independent so the alerter shuts up. You're going to start counting, and whenever you count 60 seconds, you're not allowed any leakage on your equalizing reservoir, and you are not allowed less than 5 psi per minute of brake pipe leakage. So this gauge is not allowed to move more than 5 psi. This gauge should not move at all. Here we are at about 30 seconds. $45. Five, 4, 3, 2, 1, 0. Now you can actually see this equalizing reservoir gauge has moved a little bit. So this locomotive does have an equalizing reservoir leak and cannot be used in lead. Fun little way to check that is you can actually take, if you have what, this one has out, freight, and passenger. You can't really see it because of the lighting. But if you take your automatic and you put it in passenger, see how our equalizing res just moved up a little bit? That's a good way to tell that you have an equalizing res leak. As a side note, for any train crews watching this, before I even say this, this does not supersede any operating rules for any railroad, but per the FRA, it is permissible if you have a freight train and you know you have an equalizing res leak, you can run with your automatic in passenger, because in passenger it will maintain against that equalizing reservoir leak. So per the FRA, that is permissible. Per any given railroad, it might not be. But that is the thing I did want to mention to you guys. And also, so that was the thing I wanted to mention for any train crews running this. If you run into a situation where you have an equalizing res leak, assuming your railroad doesn't forbid it, you can run with the automatic in passenger. Now you can't run, your equipment behind you does not have graduated release, so you still have to run exactly like you would a freight train. But if you run in passenger and run your brakes just like you would if you're running a freight train, it's not going to mess anything up. Now, one last thing I want to mention here, because I forgot to mention it earlier whenever we were talking about going in and out of lead, is what happens if you cut your automatic in too soon. So if I take my automatic here, cut it out, and go to handle off like we're in trail, let our pressure go all the way down. Alright, 10 psi, that's close enough. If you get a little overzealous and you cut this back in before the equalizing res pressure gets all the way up, I'll show you what happens. You'll dump your locomotive or your entire consist into emergency. can see our PCS light tripped. Some locomotives will turn the sand light on because you have emergency sand. If you cut your automatic in too quick, it will trigger an emergency application. Because if this pressure is too low, the brake pipe is gonna rapidly try and equalize. Your vent valves will see that and think you're going into emergency, so it'll dump the consist. Now, in order to recover from an emergency application, you're gonna take your automatic, go all the way over to emergency. If you wait, sometimes it takes a minute, you'll hear the A1 charging reset on this locomotive since it has one. Give it a minute. Not sure you guys will be able to hear that, but it did just reset, I think. So, you can see when you pull it back out, our PCS light goes out, and now we can recover the air of our train again. You can see also, whenever you go into emergency, your brake cylinder pressure goes higher than it can normally. Which actually, this looks like this independent needs adjusted too. It's a little bit too high. It should be 72 PSI. But anyway, that's a little spiel here about how we perform an air test, as well as a couple little things, and even a little bit of old myth busting. So hopefully you guys enjoyed that.